Let's look at a rational function on the graphing calculator and see how the graphing calculator's different tools can help us analyze that rational function. So our rational function that we have here is x minus 5 over 2x squared plus 5x minus 3. The denominator has a higher degree than the numerator, and the numerator is just a binomial while the denominator is a trinomial. Using the calculator to graph this rational function, we have an image that looks like this. Now, we are, again, not so concerned about the individual characteristics of this function yet. We'll get there. Later lessons, we'll start to talk about how different asymptotes are formed and all of that. But we're going to look specifically at those locations where this graph has some weird behaviors happening. So the first weird behavior we should notice is that as we approach x is equal to negative 3, which is right here, from the left, we see the function move downward and point down towards negative infinity on the y-axis. But as we approach that location from the right, as we move in from the positive and the slightly less negative end, and we come this way, we notice that the function points up and moves up in that direction. That is where we get what's called a vertical asymptote. There's an imaginary vertical line right at x is equal to negative 3, where that function is not crossing that imaginary vertical line. As we approach it from the left, the function points downwards. As we approach it from the right, the function points upwards. Sometimes those two sides will point the same direction and hover around that imaginary vertical line, and sometimes they'll point in opposite directions. In this one, we have them pointing in opposite directions. The same thing happens over here at what looks like x is equal to 1/2. From the left of 1/2, we have the function pointing upwards, and from the right of 1/2, we have the function pointing downwards. So it looks like we have two locations for this function where the function does not exist. We have a vertical asymptote at x is equal to negative 3, and we have a vertical asymptote at x is equal to 1/2. We could have got that information by doing a quick solving analysis of this denominator, and we would have seen that the two solutions for this denominator were negative 3 and positive 1/2. But that doesn't automatically make it an asymptote. You could see from the other lesson materials that there's also a situation where we could have a hole in the graph, which we will again talk a little bit more about in later lessons, but this one doesn't have any holes in it. The more advanced your technological resource, the better those resources tend to be at showing you holes in the graph. This one doesn't show us a hole anywhere. We don't suspect that there's a hole. A quick analysis of this denominator tells us there's probably two places where something weird is happening, and that's our two vertical asymptotes. Not to be confused with a vertical asymptote is a horizontal asymptote, which describes the end behavior of a rational function. While it looks like these two outside parts, these two end behavior sections of the rational function, look like they go up and meet the y-axis, they do not. They are getting so close to the y-axis that the calculator is unable to show that there is a difference between them. If we were to zoom in on the locations over here, where it looks like that blue rational function is touching the x-axis, and we would continue to zoom in on those locations, you'll see that it actually doesn't. And sometimes you need to go to a particular level of zoom to see that it doesn't actually reach it. Now, it does say y equals 0 because I'm sitting on the axis, but I move up a little bit and I see that I'm actually close to the line or close to the rational function at 0.01333. But I zoom in, I see that I just ride alongside that axis. I don't actually touch the x-axis, so that y-axis, that line y equals 0, I'm sorry, that x-axis, excuse me, I'm getting close to the x-axis, that line y equals 0 is my horizontal asymptote describing the end behavior. If you want to use the table function of the calculator to do a little bit of analysis, you can. If you press second in graph, that brings up the table. Here are all of the x inputs, and here are all of the associated outputs. If you just looked at this block of 11 inputs, it would look like the function is defined everywhere. However, if we go back a little bit and press up, we have the option to look at some of the other values, and we see that error situation at -3. We see where the function doesn't exist. The function does not have a value at x is equal to -3. But because of the way that this table is set up, we can't see the one that was supposedly at 1/2. You have some control over how you set up the table. And that happens in second and table set, which is the secondary option of the window button. So second table set, you can tell the calculator where you want your table to start, and you can tell your calculator how you want your table to count. So instead of counting by 1, I'm going to leave the start at -4. Instead of counting by 1, I'm going to have the calculator count by 0.5. And I can press second and go back to the table. Now I see that it's counting by 0.5s, and there's my second location where the graph does not exist, where the function does not have a value. That's my other asymptote. So the level of detail that you provide in the calculator and for the table can be beneficial when it comes to actually looking at those values and seeing where are my errors. Is it in the place that I think? Was it at 0.5 or instead of 0.4? Maybe you're not able to tell that just by looking at the picture. This helps you with that accuracy just a little bit. You also have the option in table set, if you'd like to instead of worrying about the start and the count, go down to where it says independent and change that to ask. If you change the independent variable to ask and you go back to the table, you'll notice that the table is now blank. You will type in specific X values and the calculator will give you back specific Y values. So depending on which value of X you wanted to test, it can give you different values for different locations on the X-axis. That's a good way of testing if something is actually an asymptote. I put in a 1,113 and I got a value that wasn't 0. That's an indication to me that I'm still riding alongside the X-axis, not actually touching it. Now, if you type a number that's too large, oh, even there, we got a value that's 7 zeros in it. Still pretty small. Still an indication that I'm not actually touching the asymptote. So that option where you have the opportunity to type in whatever numbers you want can be beneficial when you're trying to determine the end behavior of a graph. So the calculator could be a good tool when it comes to rational functions. You have to know how to use it. Yeah, it's one thing to look at the graph of it, but if you could be a little bit manipulative with the table and set some of these characteristics up the way you want them set up, you have a little bit more control over what values you see, and you have a little bit more control over looking at specific locations as opposed to just looking at the general picture of the graph.